Hello, I'm Sam Dare, and we are going to walk through how to tune a PID loop on an external absolute encoder with the Thrifty Novas. So I wanted to share with you guys some of the new features we've added to Thrifty Config. So one of these is you can now dynamically see the CAN usage as we type. And it's color coded based on if you had 20 devices, what would be problematic if you had the same settings for all of them. So we have our traditional configs, we have our status frames, we still have our PID, and we have our graph. Graph has been updated in quite a few ways. So the first is we have x-axis scaling now. So if we want to look at 100 milliseconds at a time, we can do that. And we can use the arrow keys to do that. We can also drag the actual window. This is really helpful for tuning PIDs, and we'll get there in a minute. We also have the absolute position integrated in here, so we can tune an internal position of velocity with the internal encoder or an absolute position, all on the app now. We also added the ability to immediately start graphing from the Run tab. And we added on our encoder tab this nice wheel here, as well as the ability to zero these and revert those offsets back if you zero it by mistake. And you can make that offset anything you want. This is particularly useful for the Swerve itself, because then you don't have to worry about a constant in your code. It's all saved on there. You just plug in via USB and find your zero it, and move forward. You can also do this over the API. So we're going to start tuning the PID of the Azimuth. So to do that, we are going to graph the applied power as well as the external absolute position. We can graph current here too, but I'm not super worried about a system with a 25-to-1 reduction like this Thrifty Swerve having current problems. So we're just going to leave that as is, so we keep our graph as simple as possible and easy to interpret. So the first thing we're going to do is we're going to increase the p-value. And we're going to start with something really, really low. So we're going to start with 0.0001. And we're going to start our graph off. We're going to reset the x-axis so it's auto scaling again. Go ahead and restart that graph. And we're going to jump to 1,000. You can see that it does in fact get to our set point, but just jumping 300 points took about a second. And what we're going to do here is we're going to do step changes. So we're going to do 0 to 90 degrees, which is about 1,000 ticks, because it's a 4096 tick encoder or 12-bit. So here you can see that when we start applying power, we then ramp off as you would expect, except it takes about 2.7 seconds to get to our set point, and we don't like that. So we're going to increase that by double and see what that does. So our p-value is now doubled. We'll restart the graph, and we'll go from 1,000, from 2,000 to 1,000, excuse me. And you can see here that once again we get to our set point, this time in about a second and a half, which we can do better than that. So we'll go ahead and stop it. And we'll keep doubling our p-value. So we doubled it here from 0.0001 to 0.0002. We'll try 0.0004. And we'll jump back to 2,000 for our step change. You can see here that we get there in a much better time span, and we're going to actually zoom in and see what that looks like. And we're going to want to zoom in on the y-axis as well. So we're going to go from 950 to 1050. Oh, my mistake. We want to go from 1950 to 2050 because our set point was 2000 there. So you can see here that as we get up to it, we are still struggling a little bit to get all the way to 2000. So we're going to continue upping our p-value here. We're going to try 0.0006. And we're going to restart our graph. We're going to jump to 1,000 and then immediately jump to 2,000 because that's what our graph is all zoomed in for right now, just for the sake of time. And you'll see here that we do get even closer to 2,000. Now we're going to try 0.0008. We'll increase that by a third. And we'll do the exact same thing. Use our arrow keys again. Now you can see we're really starting to get there. And this is the first time we've actually overshot. So we're going to reset our graph here. And even in here, you can see the slight overshoot. So because of that, we're going to start adding some D value. We're going to add a D value that's really, really low. We'll start with 1/8 of our P value. So you can already see that this is really smoothing this out, which is exactly what we intended. And we are getting there in about 180 milliseconds, which is within our defined goals. So we're going to increase the p-value just a little more and just see what happens. So if we zoom in to 1/2 second, just like we had, we can see that we're now hitting our set point also in about 150 milliseconds. And we aren't overshooting at all. We're having a nice ramp rate towards the end here and in the beginning. We're hitting about 60% of our motor speed. And really, that's about all you need for your Azimuth on a swerve drive because you have the whole inertia of the robot when you're driving. So we could spend probably another 15 minutes tuning the last 1% out of this loop. But we're actually just going to call it there for this video. And I think we've successfully demonstrated the PID controller and the external absolute encoder. This is the Redux encoder, and it works natively with no wiring changes in the Spark Max mode. And we will also be working native with the CTRE encoder. And we are working on the Thrifty Absolute encoder next. So I just want to thank you guys for your support. And if you have any questions, please let us know. Find this and more at thethriftybot.com.